So last time we saw that it was possible to destabilize a hybrid system by switching between different modes, even if the different subsystems or modes were stable or asymptotically stable themselves. In this lecture, I want to harp on this theme a little bit more. And in fact, I've called it danger beware, because this is actually something that we need to be aware of. And it's not always so easy to ensure that the overall hybrid system is stable, even if the subsystems are unstable. In fact, like I saw, we looked at a counterexample that allowed us to actually destabilize, which means drive the state off to infinity, by being unlucky or unclever in how we transitioned in and out of the different modes. So if we ignore the resets, meaning there are no reset maps, the state doesn't jump when you're making transitions, we get something called a switch system, where you have x dot if is f of x comma u, but now I have this little sigma index here, and sigma is what's known as the switch signal. So sigma is going to tell me which mode the system is in. So if sigma is 1, I'm in mode 1. If sigma is 10, it's in mode 10. Or if it's p, it's in mode p. So all I'm doing is I'm switching between different modes. And this switch signal can be rather different. It can be just random. It can be driven by time. It can be driven by things happening in the state. But it's a very general way of describing a switch system. Now, if you have that, we can actually talk about different kinds of stability. And I just wanted to point out that these things actually exist, and we should be aware of them. The first is what's known as universal asymptotic stability. And universal means that there is nothing I can do to destabilize the system. No matter what, this upside down A means for all sigma. So x will go to 0 no matter how I switch. That's called universal stability. The other notion is existential stability, which means there exists, the flipped E here is it's called an existential quantifier. It means there exists a switch signal that makes the system stable. So not all of them, but at least there is one that makes it go down to 0. And these are the two main ways in which people want to deal with switch systems. In our case, we don't have there exists a switch signal typically, or for all, we have what's called hybrid stability, in that we actually have a hybrid system that is itself generating the switch signal, and this is known as hybrid stability. So x goes to 0, not for any old sigma or for all sigma, but for the one that happens to be the one that we have in our hybrid system. So here are some results. Let's say that I have a hybrid system where all the individual modes are asymptotically stable. Well, then, can we guarantee that it is at least existentially stable? Well, clearly we can, right? Because what we do is we don't switch. If I design a switch signal that just picks one mode and then stays with that forever and ever and ever, well, we're never switching, but all the individual modes are asymptotically stable. So if all the modes are asymptotically stable, we never switch, and voila, we do have an existentially stable system. But as we have seen, they're not always universally asymptotically stable. And the reason for this is, well, this counterexample, the reason is that we can actually destabilize the system by an unfortunate switching between the modes. So what do we do about this? Well, there is something in nonlinear control known as a common Lyapunov function. I'm not going to talk about this in this course, mainly because the common Lyapunov function is an elusive beast that you can almost never find. But theoretically, that's what you're going to have to hunt for. Practically speaking, though, what you need to do is the following. First, never design unstable controllers, because then you're going to be in trouble, probably. Right? So design stabilizing controllers for the subsystems. And then we design the switching logic, meaning how are we going to switch between the different modes. And if we're lucky, or we have a lot amount of free time on our hands, we can go find or try to find these common Lyapunov functions. Now, like I said, finding that is really more art than science, in the sense that it's very hard in general to find it. So the most important thing here is really we need to be aware of the fact that stable subsystems do not ensure asymptotic stability of the hybrid system. So we need to be aware of it and test, in the sense that run it, see what happens. Do we get instabilities induced? And if we do, we need to start messing with our switching logic. But this is really key, and I cannot underemphasize the testing aspect of a hybrid system. In fact, when people design avionics software, for instance, a majority of the time is spent not on the development of the controllers, but on testing that the switching logic in combination with the controllers does not induce instability. So that's what we need to keep an eye out for.